We'll begin again our discussion of photon bubbles with Neil Turner, who will tell us about photon bubbles in high-mass star formation.
So this is some work that has been done by a fairly large group of people over the years. We've already heard from Omer and from Mitch, and we're going to hear soon from Aristotle. And some of the other people who have been involved are Peter Bodenheimer, Jim Stone, Carl York, Elliot Quattier, and just recently John Hayes. This is roughly chronological. So the most familiar source of free energy for driving motions in the surface layers of stars is buoyancy, perhaps because we have a close-by example that we can study well. But there is another source of free energy, and that's the gradient in radiation energy density, which drives the flux. And so the kind of photon bubbles that I'll be talking about are the kind that Charles Gammie pointed out could be present in black hole accretion disks, and they're related also to the ones that John Aarons discovered in neutron star accretion columns. These ones depend on the magnetic field. And here's how they work. Here's how they tap this other source of free energy. So this little grey square here is a patch of the atmosphere of the star. The gravity is pulling the material towards the center of the star, and the flux of radiation from the interior is moving upwards. And we have a strong magnetic field here at some arbitrary orientation. And to get things started, we reduce the density by 0.1% in this little elliptical region in the middle. And the lower density means a slightly larger radiation flux. And that flux tends to travel down the long axis of the lower density region. So that means you have a perturbation in the flux which has a component parallel to the magnetic field. And so that means that gas will slide along the field like beads on a wire. And so material that's initially in the middle of this little low density region will slide to the right until it hits the wall and stops. And material that's initially on the left-hand side here will slide out and replace the other gas in the middle. So although any one blob of gas just travels the width of this cavity and then stops, the pattern as a whole is going to propagate in the other direction. So if we look at a time a little bit later, the pattern has moved off to the left here. There's also the disturbance propagating to the right, but that's damped rather than driven because the radiation force is pointing in the wrong direction. So if we go to a later time, the disturbance has grown stronger, and the reason is that material is removed faster from the interior of the cavity, where you have a larger radiation perturbation, and new material comes in from the side. So the density perturbation grows over time. And here's a little movie showing what happens over the next couple of free-fall times in this little patch of the atmosphere. And each side of that initial 0.1% density perturbation becomes a shock, and we get density contrast across the shock of an order of magnitude or more after just a few free fall times. So that's how the instability works, and here's an outline for the rest of the talk. First, I'll discuss the criterion for this process to work, and see whether it's satisfied in the atmospheres of O stars. And then I'll show the equations that we're solving, the approximations that we're making, and then I'll discuss two applications of the instability. First, to the photospheres and the regions just below the photospheres in O stars, and also to the envelopes, the dusty material around the stars, which is hopefully infalling to increase their masses. So first, when does the instability grow? Well, the conditions we're interested in are where radiation pressure is at least a little bit bigger than gas pressure. This is the density and temperature plane, and there's the photosphere of an O6 star and the region below the photosphere. And the yellow shaded region here is the region where the radiation pressure is bigger than the gas pressure. So you can see that they're comparable at the photosphere, and it becomes more radiation pressure dominated as you go down. That's true in the dusty circumstellar envelope as well, even though the density is many orders of magnitude lower, and the temperature is only the dust sublimation temperature comes down. you still have temperatures that are high enough so that the radiation pressure is a little bit bigger than the gas pressure. And under these conditions, Omer and Aristotle showed that an approximate condition for photon bubbles to grow is that the radiation flux should be bigger than the gas sound speed times the radiation energy density. And that's easy to satisfy here because the definition of a photosphere is that the radiation becomes free streaming. So the radiative flux is roughly the speed of light times the radiation energy density. The speed of light is much bigger than the gas sound speed. So this condition is satisfied by orders of magnitude at the photosphere. The other condition, of course, is that you have to have a magnetic field, and preferably a fairly strong one. And everybody knows that massive stars don't have magnetic fields because they don't have convection in their surface layers, so there's nothing to provide dynamo action. But what everybody knows isn't necessarily so. Here's a spectrophotometric observation from a few years ago, and Donati et al. Looked at Theta 1c Orionis, the illuminating star in the Orion Nebula, and at two different rotational phases they see different Stokes V signatures. And by modelling this, they found that it's consistent with a kilogauss, roughly dipole magnetic field. So that's not what was expected. On another star, a slightly cooler star, B0 roughly, they got data for a large number of rotational phases, and they were able to reconstruct, with some assumptions, the surface magnetic field. And again, it's quite strong, but it's slightly higher order, sort of m equals 5 is the strongest component of the field here. And this is static over a couple of years. So they're suggesting that it's not being currently generated, but it might be a fossil. There's also evidence from the X-rays. This is from a big Chandra survey of Orion. And Seltzer et al. Found that most of the O and early B stars in Orion have either rotational modulation of the X-rays on the period that's known from optical studies of the same star, or they have variations in hardness on the rotational period, or they have flaring. So all of these things suggest magnetic fields. So perhaps the magnetic fields at the surfaces of O stars are quite widespread. There are also magnetic fields in the circumstellar envelopes, and these are studied using Zeeman polarization of maser emission, because the maser emission is very bright, and so we can get very detailed information about it, if only at isolated spots in the envelopes. And the magnetic fields are 10 milligauss up to a Gauss or so. And they've been seen by several groups. This is a recent result from Lemmings et al., but Sama et al., and there's a classic paper by Fiebig and Gustav, and all these people have found similar strengths for the magnetic fields in a variety of high-mass star-forming regions. And the spatial scale here is 100 AU or so. And the gas pressures that are expected in this region are similar to or less than the magnetic pressures that you get for these field strengths. So the magnetic fields are dynamically important. So on to what we've done to look at how photon bubble might act here. We're solving the standard equation of hydrodynamics in blue. We make it MHD by adding the Lorentz force and the field evolution equation. And then we're treating radiation in the same approximation that Omer discussed. We're using flux-limited diffusion, frequency average, so we have just one frequency bin, and the flux is proportional to the gradient in radiation energy density, with a flux limit of lambda that's 1/3 where we're optically thick, and then falls to 0 where we're optically thin, so as to preserve causality. And perhaps this is good enough for the situation that we're looking at where things are optically thick, and most of the opacity is due to electron scattering. And notice also that we do include the radiation force in the momentum equation for the gas, and that's very important, of course, for this instability. So let's look at the first application, which is to the photospheres of O stars. And there's a problem that photon bubbles might shed some light on, and that's that there don't seem to be any O stars that are pole-on. There are none where we're looking at the rotational pole, apparently. And this is a problem that's been known for a long time, going back to Sletterbach in the 1950s. So this is the projected rotational velocity as a function of spectral type for O stars of luminosity classes 3, 4, and 5. The problem is that there's a gap down here. There are no upper O stars with relatively low projected rotational velocities, as would happen if we were seeing them pole on. So there's some kind of a gap down there, and the minimum speeds that we see for the projected rotational velocity are the sound speed or even a little bigger. So the preferred explanation, rather than the universe playing a trick on us, is that there should be some extra source of motion in the photosphere. But what? Who knows? So to see whether photon bubbles could provide this extra motion, we've done some box in a star calculations. So our little patch is 1% or so of the star's radius, and we've put it at the magnetic equator. So we have a magnetic field that is perpendicular to the radiative flux, and we put in little 0.1% density perturbations, and let things go for a few free-fall times, and the photon bubbles grow up into shocks again. Here, because we have horizontal magnetic fields, material traveling to the left, or shocks propagating to the left and shocks propagating to the right, both grow. Neither one is particularly favoured. So we end up with cross shocks. And then once we get to density contrasts of a factor of a few and speeds comparable to the sound speed, things saturate. There's no more growth. So the time scale involved here is a few hours, maybe 10 hours. So here is a picture of what's happening at just one of those shock fronts. This is from Mitch's work. So the black line is the shock front, and the blue line is showing the background magnetic field. And material that has just passed through the shock front is dense, so it has a lower radiation flux. And so gravity wins out over the radiation force there. So this material is sliding down along the magnetic field line. But it's not quite in hydrostatic equilibrium behind the shock front, and the radiation force up somewhere around here, the radiation force begins to win out because you're at lower densities, and so there this material begins to be pushed back up the magnetic field line because the radiation force wins out over gravity there. So this material is going to be accelerated back up the field line until it meets the next shock in the train. So although any one blob of gas slides down until it begins to be accelerated back up by the radiation and then slides down again, so it oscillates back and forth, just like in the linear instability. But the shock pattern as a whole is going to propagate down the magnetic field lines. This is happening for shocks moving both to left and to right in our calculation with horizontal fields. And here are the saturation amplitudes. So the calculation that we looked at just now was for theta 1c Orionis conditions at the photosphere. And here's what happens if we reduce the effective temperature. So we look at late O stars and early B stars. And the saturation amplitude, so the units here are ergs per cc for the kinetic energy, domain average. That's a function of time, so here's about a day. And you can see that the saturation amplitude becomes lower and lower. And so here the speed is 30 kilometers a second or so at saturation. And here it's almost an order of magnitude down, and here down further again. And so that's consistent with what we saw for the late O stars and the early B stars not having significant extra motions in their photospheres, just the mid O stars and the early O stars. And the other thing to notice is that even for our O6 star, the amplitudes at saturation are an order of magnitude below the magnetic pressure. So the kinetic energy, the ram pressures in the shocks are not enough to bend the magnetic fields. Fields get ripples on them, but they are not torn apart. So now to the other application, which is to the circumstellar envelopes. And these are a bit mysterious because they have very high extinction. It's difficult to see what's happening inside them. They're also mysterious because they're a little further away than the nearest low-mass star formation regions, so we don't have such good spatial resolution. But what we do see is that most of the ones that were found initially were associated with maser emission of some kind, and so now this is a way that people find them. Just go and look for the maser emission, which is bright. And what's seen is that the gas is warm. It's 100 to even a few hundred degrees, so much warmer than is typical in molecular clouds. And another thing that's different about them is that they have significant non-thermal line widths. The spectral lines from the molecular gas have widths of a few up to maybe 10 kilometers per second. And that's much bigger than the sound speed, which is maybe about 1 kilometer a second. So again, there has to be something driving motions inside these hot molecular cores, which presumably have massive stars growing at the center. So here are some problems where photon bubbles might be useful. One is these motions. The other one is the origins of the maser emission. So people who do microphysical models of the maser emission find that you get good conditions in shocked gas. It can be either weak shocks, just a little bit faster than the sound speed, or it can be very strong shocks, either one. But the mystery is where the shocks are located. And over the years, people have considered they might be connected with the outflows from the massive stars, the interaction of the outflow with the surrounding gas. They might be related to the disk. Perhaps there's material crashing in on the surface of the disk around the massive star, or perhaps they're related somehow to these motions in the hot cores. And then the third problem is with the Eddington limit. So if you take spherically symmetric accretion onto a star that's increasing in mass, and you consider the opacity from interstellar dust grains, then when you get up to 30 solar masses or so, you reach the Eddington limit, and the incoming material is stopped by the radiation. So to get around this problem, you have to make the outgoing radiation anisotropic somehow, and perhaps photon bubbles can be helpful there. So to look at this problem, we're doing a box in an envelope type calculation. So here, this is not to scale. This is maybe sort of 10% of the radius, the distance to the star. The star is the little blue circle here, and the distance to the star is about 400 AU. And the box is located roughly at the distance where the star's radiation is destroying the dust, sublimating the dust away. So in here, it's ultraviolet. Out here, the dust is present, and so the ultraviolet is very quickly absorbed and converted to infrared radiation. And we're looking at that regime, the infrared radiation, just outside the dust destruction front. And we're going to look at cases where we have either a horizontal or a vertical magnetic field. So first, let's look at the case with horizontal fields and look at the linear growth. And so up the top here, we're looking at the growth rate, which is shown by colours, as a function of wave number. And this is from solutions from Omer and Aristotle's linear dispersion relation. So wave number 0, 0 is here, and horizontal wave number increases to the right, vertical wave number increases upwards. So we have the brightest green colours in the middle here. So this means that waves propagating about 40 degrees above the horizontal are growing fastest, and they're growing by a factor of a few hundred per 1,000 years. So that means that in the free fall, 1,000 years is not too different from the free fall timescale through the envelope. So from, say, 1% density perturbations at the start, you can easily get order unity density disturbances by the time the material's fallen through. And then the other panels are results from numerical calculations with different resolutions. And things are obviously much noisier here, but again, the growth rates are highest somewhere around 40 degrees above the horizontal. Part of the noise comes from these vertical stripes that you can see, for instance, in the 128 squared calculation. And that's because we have global oscillations of the atmosphere, which are not growing. But once we've removed those as best we can, the underlying growth rates are are sort of similar to what you get in the linear analysis.
Excuse me, what kind of code are you using and how do you treat the dust, the sublimation and the radiation?
We're using Zeus, and we've located things just outside the sublimation radius, so we're not worrying about the sublimation itself. We did have to worry a little bit about the coupling of the magnetic field to the gas, and a little bit about the thermal coupling of the dust and the gas, but both of those things turn out to be good.
And it is flux limited diffusion.
Yes, that's right. One other thing to be aware of is optical depth effect. So if we go to very high wave numbers, very far from the origin out here, then the optical depth per wavelength is less than 1, and so disturbances in the density shouldn't produce a disturbance in the flux. And so we shouldn't expect the kind of photon bubbles that we're looking at here to be present out there. This means that at our highest resolution here, we have we've resolved almost all of the modes that we expect to have high growth rates. The other things to be aware of are that to be growing fast according to linear analysis, you need to be outside this line here, which means you need to have wavelengths shorter than the gas pressure scale height. And then if you do that, then you can get growth rates up to the free fall time over the gas pressure scale height. So that's fast. Now let's look at the nonlinear development. So here's a movie for the case of an almost vertical magnetic field. The field is just 3 degrees away from the radiation flux vector. And this movie is short because things happen fastest in this case. Because here, because the magnetic field and flux vector are almost parallel, so the perturbation in the flux has the maximum driving effect. So the growth rate is highest. Here's where you achieve that maximum growth rate, so the growth time scale is similar to the free fall time scale. And at the end of the movie here, what we see is that we have the shock fronts that are almost parallel to our other two vectors in the problem. And the density, the reason this calculation is ended is that the density has grown very, very low here in regions near the bottom of the box. So we have basically disrupted our initial condition in this case. Another thing to notice here also is that the shocks are not propagating very fast. They, at the end of the run here, they're almost where they were when they started. And the reason again is that the two vectors are close to one another, so the component of the gas velocity that's perpendicular to the shock fronts is relatively small. So that's why the propagation speed is slow. So there were those three problems that we wanted to solve. We wanted to look at the small-scale motions in hot molecular cores. We wanted to look at the possibility of shocks and maser emission, and we wanted to look at the Eddington limit. And the first of those problems we can check by looking at the top panel here. So this shows the maximum and RMS speed as a function of time in thousands of years. And the left column is for the case of horizontal field, and the right column is for the inclined field case. You can see that before our runs in, we get speeds up to a couple of kilometers a second here, or 4 kilometers a second here. And let's see, we discussed the reason that this run ends. This run ends because in the horizontal field case, the field lines bend up through the top of our box, which is open, and we begin to lose material. So again, the instability destroys our initial condition. So what we think is going to happen is that if we were to do this calculation in a larger box, then the scale of the shocks, the separation between the shocks would ultimately be set by the strength of the magnetic field. When the shocks grow too far apart, you would just bend the magnetic field and destroy the initial configuration. But what's clear is that to start out with, you can get, so this means speeds of 2 kilometers a second means velocity differences across the shocks of 4 kilometers a second. You can certainly match the velocity dispersions that are seen in hot molecular cores. Another thing to notice here is that the Alfvén speed, which is the dashed line, is roughly constant until almost the end of the calculation. And the reason is that the gas is sliding back and forth along the field lines, so the field strength is not being changed. So although we've assumed a tenth of a Gauss field to try and match those observations, we're not violating that because we still have the same field strength towards the end of the run. And then down the bottom here, we're looking at the third of those problems, the Eddington limit problem. Here's the maximum and mean flux in the box. And the flux increases above the Eddington limit by the end. So the material keeps on falling towards the central star, even though the flux through the box has increased above the Eddington limit. So there's some hope that we can get around this problem of stopping accretion before you reach the masses of some of the observed stars by punching holes into the envelope. So this is from a radiative transfer calculation by Indebito et al. And so this is what we think the envelope might look like after photon bubbles have done their work. They're going to punch holes here and there in the envelope, and so what you see when you look in will depend on exactly which line of sight you happen to be looking along.
Sorry, I didn't understand that. I mean, there is no hot core where you can look like this in the near-infrared into the core. So what is this showing now?
Well, this is on spatial scales smaller than are easily resolved at the moment. And this is also, there will also be foreground extinction that will make this difficult to see in the way that he's shown in his calculation. But this is a representation of what we think might be happening very close to the star. So we've looked at one of several kinds of photon bubbles. Perhaps I should say a little about the different kinds of photon bubbles that there are. So I know of at least three kinds. There's the kind that Ed talked about earlier today. There's also another kind that Mark Krumholtz has worked on, where you have radiation from a massive star basically blowing a balloon into the surrounding medium, and then you could get a Rayleigh-Taylor type instability, and perhaps you could have erratic accretion in that case. That operates on kind of the global scale, but then you can also get these small-scale instabilities which require a magnetic field. And it's unclear at this point just what the relationship is between these different kinds. But for instance, these small-scale instabilities, which operate here on scales of 10 AU or so, that's where the fastest growth occurs. They could act as a seed, for instance, for a Rayleigh-Taylor type instability on larger scales. And these small-scale instabilities are fundamentally different from convection, in the sense that the source of free energy is not buoyancy, but it's the radiation flux. That's where the energy comes from to drive the motions. And the linear results and the numerical results all agree that if you look at wavelengths less than the gas pressure scale height, which can be much less than the radiation pressure scale height, then you get fast growth. You get growth on the free fall time scale. In the photospheres of O stars, the instability saturates with weak shocks, and that's about what's needed to explain this apparent lack of pole-on O stars. And also the instability can be present in the dusty envelopes around young massive stars. And there it can provide stirring at supersonic speeds and make the envelopes conky to perhaps let the radiation escape. And it can provide the shocks that could be the environment for maser formation. That's all.
Questions?
Maybe criteria be worked out, the one which was mentioned at the very beginning, in terms of critical beta, just to radiation pressure ratio.
That criterion depends on certain gas to radiation pressure ratio. It changes. Also, that criteria presumes vast radiation pressure, much lower than that. Okay, right. So, but if that's not the case, then that becomes a more important.
You have a question?
When you showed your cartoon illustration in the beginning, I got all of a sudden distracted by something else. But then it looked similar to the explanation of the instability that Balbus and Stone also looked at with thermal conduction along field lines, where the free energy is in the vertical temperature gradient. Yes. Is that the same mechanism?
Perhaps it's related. Let's see.
Because he also couples, of course, different regions with different temperatures by conduction along the magnetic field.
Yes. I mean, here you do have flow across the magnetic field because the photons are free to slip across. But it is related in that the component of flow along the magnetic field is important for driving the instability. And it is related also in the sense that if you were to somehow get to equilibrium, then that equilibrium would mean having a uniform radiation energy density and so uniform temperature. But I think that if you were to get to that final state, it would be different from magnetothermal instability because there, under at least some conditions, they've gotten the magnetic field ends up being aligned parallel to the original temperature gradient. Whereas that wouldn't necessarily happen here because the photons can slip across the magnetic field lines.
But the slippage across would lower the efficiency, would it not?
It does do that if in this case with horizontal magnetic fields. If the magnetic fields are close to the flux vector, then there's basically no reduction from that effect.
Other questions? If not, let's thank our speaker again.
Try it now. Is it on?
It's not.
It's like a circle, that's similar. And there's a circle, there's a boundary there.
Suppose that has to do with your
Computer?
No, that's how much it should.
Okay, thanks.
Yeah, sure.
I'll look at you and ask if you can
And you put in the field, and the field takes over. That's what happens. So that's fine with me.
Now we're going to hear from Aristotle Socrates, who will tell us about super Eddington luminosities from super Eddington accretion, powering ultraluminous X-ray sources, and stellar mass black holes.
Right, thank you. So ultraluminous X-ray sources powered by stellar mass accretion or super Eddington accretion onto stellar mass black holes. So ultraluminous X-ray sources are a relatively new class of sources and that have gotten quite a bit of attention recently. And the reason why that is because due to their very large inferred bolometric luminosities, people think that they are the seats of intermediate mass black holes. However, and of course that would be very, very interesting because we know there are two classes of black holes. There's the stellar mass black holes who have masses of order 10 solar masses, and the supermassive black holes which have masses of order millions to billions or more solar masses, and those are thought to power quasars. So these would serve as the missing link in between the two very well-developed populations. However, this work takes a different tack. We're going to go about this a little bit more conservatively and say that it's possible to power ultraluminous X-ray sources with stellar mass black hole, accretion onto stellar mass black holes, and that accretion is super Eddington and radiatively efficient. And this talk is going to basically outline a blueprint of how you go about doing that. So this work is done with my former office mate and colleague, but still he's currently my friend, Shane Davis, from UCSB, and now he's at the Institute for Advanced Study, and he's a Chandra Fellow there. And we both had a common thesis advisor, who I won't name. Okay, so outline. So let's start off with an outline. So first I'm going to tell you what are ultraluminous X-ray sources. I'm basically just going to define them. And then I'm going to tell you why they're interesting or why people think they're interesting. And in order to do so, I have to give you a bit of an overview of the observations and theory of ultraluminous X-ray sources, or what's the current state of the art in observations, what do we know about them, and what are the most basic explanations of them. And then I'm going to give you a basic idea of our ULX model. And then if we have enough time, I'm going to try to tell you about what is the basic flow structure or mechanics and radiation mechanisms of our model, and then I'll summarize. So what are ultraluminous X-ray sources? Well, ULXs, so that's what we'll call them from now on, ULXs are defined as extragalactic, off-nuclear, bright X-ray point sources. Okay, they display short-term variability, and by short-term, I mean of order days to weeks. So this rules out that they could be a supernova remnant, for example, because supernova remnants have characteristic scales, or length scales, of order a tenth of a parsec or a parsec. So if you see variability in the total luminosity of these objects of order days to weeks, that rules out the fact that they could be supernova remnants, because nothing can oscillate faster than the light crossing time. So this implies that there's some type of X-ray binary phenomena. And ULXs are located in both spiral and elliptical galaxies, but the most luminous ULXs, and the ones we're going to be talking about today, seem to track star formation. Okay. So why are ultraluminous X-ray sources interesting? Well, most of them are not, actually, and that's just because of what the definition of an ultraluminous X-ray source is. And so Fabiano, in 1989, she declared that, or defined an ultraluminous X-ray source as anything in a galaxy that's not our own that has an inferred bolometric luminosity of 10 to the 39 ergs per second. However, the ones that are interesting and the ones that we're going to study is a relatively small fraction of that population. And the reason why they're very interesting is because they're unusually bright. And the brightest ULXs are found in spirals, galaxies, or that's kind of a shorthand for saying star-forming regions. And their inferred bolometric luminosities in the X-ray band of 0.2 to approximately 10 keV is of order 10 to the 40 ergs per second or greater. And there's about a couple dozen of these sources. And why is this an interesting number? Well, note that for a 10 solar mass object, 10 to the 40 ergs per second is of order 10 times the Eddington limit for that object. So this leads us to two uncomfortable yet unavoidable explanations. That is, if we accept that ULXs are X-ray binary in nature, and that they are unbeamed. I'm not going to get into a detailed exposition of why I think ULXs are unbeamed, but if we have enough time at the end of this talk, we can talk about it. So if we assume that they're not beamed, that means that they're emitting isotropically and they are X-ray binary phenomena, then one conclusion the first conclusion, and I think the most exciting conclusion from an astronomical point of view, is that ULXs are powered by sub-Eddington accretion onto intermediate mass black holes. And by intermediate mass black holes, I mean of order 100 to 100,000 solar masses. And of course, this is interesting from an astronomical perspective. The second conclusion is ULXs are powered by super Eddington accretion onto stellar mass black holes, with a characteristic mass of order 3 to 30 solar masses. And this, of course, is interesting in terms of the basic physics of accretion. How does an object accrete and emit above the Eddington limit in a relatively steady-state fashion? So Either way, ULSs are worth studying. So this is new trends in radiation hydrodynamics, but I mean, almost every other talk is about, people have been talking about discussing the Eddington limit, which is the most basic and one of the oldest concepts in radiation hydrodynamics. And so the issue with this is, well, why is it difficult for an accretion flow to release binding energy and emit above the Eddington luminosity? Well, the typical way of thinking about the Eddington luminosity, which is of course correct, is to just consider hydrostatic balance. And if the radiation force exceeds the gravitational force, the object will blow itself apart. However, there's yet another constraint in accretion flows, or one studies a system that's releasing gravitational binding energy, that has to do with the Eddington limit, and this is called the photon trapping problem. Okay? So this is how it works. The flow becomes critical when the radiative cooling time is of order the viscous time, which goes like R over the inflow velocity. And for radiatively efficient Sikorsky-like accretion, this occurs when the accretion rate is of order the Eddington accretion rate. So how does this work? Well, the radiative efficiency of an accretion flow is which we'll define as eta, is of order 1 over Rn, where Rn is the innermost stable circular orbit, or the radius at which you can release gravitational power and convert it into photon power. So once you approach the Eddington limit, when the accretion rate is of order the Eddington accretion rate, the innermost stable circular orbit is of order the trapping radius, where the trapping radius is defined by this, the radius at which the inflow time is equal to the radiative cooling diffusion time. So what happens if you pump up the accretion rate, such that the accretion rate is much, much larger than this Eddington accretion rate? Well, what ends up happening is this trapping radius moves out. So for every proportional increase in the accretion rate above the Eddington accretion rate, the trapping radius moves out proportionally. And since the radiative efficiency goes like 1 over the inverse of the radius at which you can emit efficiently, the overall net radiative efficiency of the flow goes down, and your luminosity is pinned to the Eddington limit. Now, this picture is the result of local dissipation. And what does that mean? Well, you start off with some matter that has gravitational binding energy with respect to the central source, gravitational source being the black hole, and somehow you randomize that gravitational binding energy. That binding energy turns into heat locally and then escapes by photon diffusion to the observer eventually. So that's what we call local dissipation. So this whole idea of trapping, the fact that the black hole can actually swallow all the accretion power, comes about from this idea of local Sikorsky-like dissipation. Okay? So it's hard out there for a super Eddington disk. So this is one of the most compelling reasons to adopt the intermediate mass black hole scenario. So there's another line of argument that compels people to adopt the intermediate mass black hole scenario as well. And that comes from observation. So many of the ultraluminous X-ray sources, the brightest ones that we were talking about, the ones that have luminosities of order 10 to the 40 ergs per second, have a cool thermal disk-like component. Okay? And we'll get to why there's an emphasis in this word component. The characteristic temperature of these thermal disk-like components is of order 0.1 to 0.5 kiloelectron volts. Now compare this with the following. A characteristic disk temperature of order 1 keV for a 10 solar mass black hole that's accreting and releasing photons at the Eddington limit. Or a characteristic disk temperature of order 0.01 keV for a supermassive black hole of mass of order 10 to the 8 solar mass black hole, of order 10 to the 8 solar masses, that's accreting and releasing radiative power at the Eddington limit. So this implies a larger emitting area than stellar mass black holes, but a smaller emitting area than supermassive black holes or quasars. So this really does imply that these are intermediate objects, or in other words, intermediate mass black holes. Just to hammer this point in, more specifically, the accretion power, we'll call it accretion power per unit area, we'll call it F plus, or the surface dissipation is equal to the viscous stress times the rate of strain integrated over the disk. We're ferrous, so we just multiply it by h of the disk, the height of the disk, and you match that with sigma T effective, which is thermal black body emission. And what you see is that most of the gravitational power comes from very close to the hole, since the effective luminosity of the disk the luminosity of the disk is proportional to 1 over the radius. And that's just because gravitational binding energy goes like 1 over r. So the characteristic disk temperature scales like 1 over the mass, 1 divided by the mass of the black hole to the quarter power for a constant Eddington ratio, since for black hole systems, the characteristic radii of the system just scales with the mass of the black hole. So therefore, intermediate temperatures as observed in ULXs really do imply intermediate masses. But let's take a closer look at the observations. So, I know you can't see this, but I'm showing it anyway.
You are.
Okay, so these are the spectral properties of highly studied XMM and Chandra ULXs, and the ones with luminosities of order 10 to the 40 ergs per second or larger. Okay, so all of these are just located in very local galaxies, distances of order 10 megaparsecs away. Okay, and how people fit the data for these ULX, the spectra of these ULXs, is they say, well, there's this characteristic thermal disk component that has some characteristic temperature, and there's a power law, which we'll get to what the meaning of that power law is. And that power law is in the hard X-rays, or at energies that is larger than the characteristic disk temperature. So the parameters that go into it is the characteristic disk temperature, gamma, which is the spectral index, and how it's defined here, the spectrum in the spectral index in X-ray astronomy is defined differently than the spectral index in radio astronomy. Here we define gamma as if you have a gamma equals 2 power law in mu f nu, it's flat. And the other parameter that goes into describing the data is a fraction of power in the power law component, in the hard power law component, divided by the total power. So let's look at what this table shows. The characteristic disk temperature. It's of order 0.1, 0.2, 0.15, 0.3 keV. So those are intermediate temperatures. However, the most important thing about this is this number. F power law over F total. What is the fraction of power that comes out in this hard, non-thermal power law emission? That fraction here, 0.74, 0.63, 0.85, 0.77, 0.68, 0.91. The power law component of these ULXs, these brightest ULXs, the hard, non-thermal, presumably Comptonized emission, is the dominant component in the SEDs, or spectral energy distributions of this object. So, let's hammer this in again, or even harder. So, let's look at 2 examples of extrapolated spectra. So clearly these are not thermal emitters. So the blue is a spectra of one source and the red is a spectra of another source. So the dotted lines are the thermal disk components, and this dashed line is the power law components, and the composite is the solid. So clearly these are not thermal emitters. Even graduate students from UC Santa Barbara could figure that out. These are not thermal emitters. So this power law component, so you have to, and really understand this, you have to understand what's going on. Where's this power law component coming from? So this power law component presumably comes about from Comptonization of some form, either thermal Comptonization or non-thermal Comptonization. And the typical fraction of power released, photon luminosity released in this power law, in this hard power law, is of order 70 to 90%. Okay? So how does this Comptonization work? Well, what the easiest picture is, or the typical picture is, well, you have a black hole and you have a cool optically thick disk, and there's an adjacent hot corona. and the characteristic temperature of the corona is of order 10 to the 9 degrees Kelvin, and the characteristic optical depth is of order 1. And what happens is you have a soft disk photon coming from the disk, and what it does is it interacts with hot electrons in the corona. So when the cool disk photons interact with the hot coronal electrons, their power gets amplified by the inverse Compton effect. And the resultant spectra, which you can kind of understand how it's shaped by the statistics of Fermi acceleration, takes the form of a power law. So the soft input comes from the disk, and the resultant spectra is a power law. And if it's thermal Comptonization, there's a cutoff at the temperature of the corona. So the only thing that you need to know is what is the covering fraction in order to understand what the shape and magnitude of this Comptonized component is what is the covering fraction of the corona, what is the temperature of the corona, and what is the optical depth of the corona. Now, this is the most important point about this. This picture, okay, of Comptonized emission coming from a corona can only exist if binding energy is released non-locally. What does that mean? Well, that means, you're randomizing gravitational binding energies here somehow. Okay, it could be some type of instability like the MRI, magnetorotational instability. But somehow, that binding energy gets out of the disk and dissipates itself in a relatively diffuse region. That's what non-local dissipation is. And that has nothing to do, that transport mechanism, or that phenomena has nothing to do with the Thomson cross-section. Okay, and so this, it seems, like I just said before, this dominant spectral component in ULXs is hard Comptonized emission. Okay? And in order to have hard Comptonized emission, you most likely need a corona. And in order to power a corona, you need non-local dissipation of gravitational binding energy. And that has nothing to do with the Thomson cross-section, and so that should have nothing to do with the Eddington limit. Okay? So, an early summary. The majority of the radiative output in bright ULXs does not occur locally. That's just an observational fact. Okay? Therefore, what that implies is that the observed thermal disk emission at these intermediate temperatures, which is a subdominant component of the ULX, the interesting ULX spectral energy distributions, it is not easy to go from characteristic disk temperature to black hole mass. Because the dominant form of release of gravitational binding energy is not disk-like. And since the majority of the gravitational binding energy in ULXs is released in a corona, the trapping problem is overcome, and that's just because whatever the transport mechanism is for energizing the corona has nothing to do with the Thomson cross-section. Thus, the trapping problem is overcome, and the Eddington limit loses some, but not all of its meaning. So, the trapping problem is really the Eddington limit for an accretion flow that has to do with radiative equilibrium. But still, there's the Eddington limit that has to do with hydrostatic balance. So what this is saying is, there's two Eddington limits, and it has to do with the cross-section of photons scattering off electrons for accretion flows. So there's two Eddington limits in accretion flows. One of them is this radiative equilibrium Eddington limit. The other is the hydrostatic balance Eddington limit. What this is saying, or what we've said so far, is that ULXs are getting around the radiative equilibrium Eddington limit, or the trapping problem. But we haven't, and I haven't told you how or why they can get around the hydrostatic balance Eddington limit. If we have time, we'll get to that. So with all this together, this provides motivation to pursue models of bright ULXs powered by radiatively efficient super Eddington accretion onto stellar mass black holes. So what's the basic picture of this model? So here it is. So this model is divided into two regions. Region 1, which you can call the active region, and region 2, which happens further out, So the situation is you have a stellar mass black hole here, and the stellar stellar mass black hole is orbiting a massive star. Okay, so it's in a high mass X-ray binary. And it's pulling matter off of the massive star. And out here somewhere, there's some type of disk that has some accretion torque that's providing accretion to the black hole. Now, in region 1, where most of the gravitational power is released because it's closer to the black hole, because again, gravitational binding energy goes like 1 over r, this is what happens. Well, you have accretion through a relatively thin disk, but the binding energy is being released outside of the disk. 90% of the binding energy is released outside of the disk. The characteristic temperature of this corona where the binding energy is released is of order 100 keV, and the optical depth is less than 1. The characteristic disk temperature is of order 1 keV, and the most important thing is that the albedo of the disk is of order 1. Okay, and this has to work in practice, not just in principle. It has to work in practice. And why is that? Well, so this is kind of how the flow of energy happens. You randomize the gravitational binding energy through some accretion torque, which allows the matter to flow in. The binding energy is dissipated here in the corona. It heats electrons to temperatures of order 100 keV, which Compton upscatters soft disk photons, whose characteristic temperature is of order 1 kiloelectron volt. Now, every time, in order to get up to 100 kiloelectron volts and take out this large amount of gravitational power, the photons from the disk have to stay in the corona for a relatively large amount of time. Now, every time a disk photon, or a photon in the corona, scatters with an electron, it has the opportunity to go either up or down. If it goes down, it cannot be absorbed by the disk. Because if it's absorbed by the disk, what will happen is it will get reprocessed into thermal emission, and half your power is going to come out as soft thermal emission. So, which is, as I said before, in violation of the observations. So you need this to be, this disk, or at least the top skin of the disk, to be a very good X-ray reflector. Now, in the outer region, well, the outer region is basically defined as a region in which the trapping problem is no longer a problem, because you're far enough away from the black hole. And here, the characteristic will work out that the characteristic disk temperature is of order 0.2 keV, and the photon power results from some combination of viscous dissipation or reprocessed emission from a corona. Okay. So, you have to make sure that you get the binding energy out of the disk. Okay? You have to make sure it comes out. You can't let that randomized gravitational binding energy get swallowed by the hole. So, how does this work? Well, in order to do that, you have to say, well, let's put some of this binding energy, or most of this binding energy, dissipated outside the disk, and then recalculate the disk structure and see if it works. So how do you go about that? Well, you say, the dissipated gravitational binding energy in the disk goes to the same value times 1 minus F, where F is a fraction of power that's dissipated in the corona. So if F is 0.9, then that means only 10% of the gravitational binding energy is dissipated in the disk. Okay, and then you match that to blackbody emission. And then after that, you just assume that everything else is the same. So this is nothing new. This is Princeton and Zdarsky 1999, Hart Marashi 91-93. So you just assume everything else is the same. So the accretion stress tau r phi, or accretion torque, goes like alpha times P. Alpha is a Shakura-Tsuniaev parameter. P here is a radiation pressure, which is also the total pressure, and the radiative flux follows a radiative diffusion law because it's optically thick. Now, what is the time scale at which you can remove gravitational binding energy out of the disk? So one good time scale is, well, it's the sound crossing time. So this is kind of a good lower limit in which you can remove gravitational binding energy out of the disk. If you move it out of the disk any faster, you might disrupt the whole structure of the disk. And what you want to do is you want to compare this time at which this characteristic time scale in which you can move binding energy out of the disk with the advection time of the disk with the new disk structure in which only a fraction of the binding energy is deposited in the disk. And so the ratio of these two has to be larger than 1. That is, the advection time has to be larger than the sound crossing time at every given radius. And so if you put in the numbers, typical numbers, alpha of order 1, a characteristic radius of order 12 gravitational radii, so this corresponds to a non-rotating black hole. M dot is of order 175, that's bad notation. 175 is of order 10 times the Eddington accretion rate for a non-rotating black hole, and the fraction of power dissipated in the corona of order 0.9, so 90% of the power is dissipated in the corona. You get that this ratio is of order 5 or 10, so it works out. So what is, you can say, okay, you're invoking a corona, and that's fine, but what is causing the corona? Okay? And the real answer is nobody really knows, and probably this is why we're having this conference in which these people are talking to solar physics people. So people have ideas for what causes the corona, but these are really old ideas. These ideas are like, they could be waves, or it could be magnetic fields that bubble up and dissipate in the corona through some reconnection process. And these are, again, old ideas, and they really just come from observations of the solar chromosphere and corona. And the real answer is nobody really knows what the mechanism, the physics behind it actually is, quantitatively. But nevertheless, we know from the observations that there is some mechanism at work, because the spectra of these objects are so non-thermal. Okay, so as I said before, one of the main key points is the albedo of this disk has to be very high. It has to be very close to 1. So you have to basically, in order to do that, since photoelectric absorption is the only form of opacity on the skin of the disk, absorption opacity on the skin of the disk, what you have to do is you have to figure out what is the ionization state. And then from that, calculate what the absorption optical depth is. And then from that, calculate what the albedo is. So how you go about doing that is saying, well, there's just one, in order to do this in a very simple way, you say, well, there's just one hydrogenic state. All the metals are collapsed into one hydrogenic state of one ion. And in this case, the ion is iron. And the ionizing flux from the disk has to be so large that it totally ionizes the skin of the disk, such that there's very little of that hydrogenic state of iron left. And so what you do, you just say, okay, do it in a one-zone model, just take a character. So what you do is you say photoionization is equal to recombination, and that gives you what the ionization fraction is, and it's of order 10 to the 5 near the black hole, where most of the gravitational power is being released. And then if you realize that, again, the only source of metals for these objects is iron, because carbon, nitrogen, and oxygen are totally ionized for stellar mass black hole disks, because the characteristic disk temperature is of order 1 keV. So that means the only thing around is iron, which is relatively low in abundance. This allows you to calculate what the albedo is in the two-stream approximation. And if you work that out, the albedo of the disk near the hole is of order 0.53. Very, very, very high. And the reason why that is because you're raining down on it a super Eddington flux of ionizing photons. So this picture is, the picture that we have here is not without precedence. So the normal, the current paradigm of black hole X-ray binary accretion is this thing called the state transition phenomenologies. And how that works is, well, there's this, for normal sub-Eddington black hole X-ray binaries, there's the low hard state and there's the high soft state. And in the low hard state, the luminosity accretion rate is very, very low, 1% Eddington. And most of the power is dissipated in some very hot coronal-like region. Some people call this even an ADAP, which is an advection-dominated accretion flow. But the main point is that most of the power comes in hard Comptonized emission, and a very subdominant component comes in thermal emission. Then you go into the high soft state, where the luminosity is relatively high, but the spectra is relatively soft or disk-dominated. So here's the high soft state, which is disk-dominated, and there is some coronal emission of order 1 to 10% of the total power. Now, if you pump up the accretion rate higher, you go to what's called the very high state. So here in the high state, the accretion rate or luminosity is of order 10% Eddington. In the very high state, it approaches Eddington. Okay, and so when you go up, you pump the accretion rate up higher to the very high state of galactic X-ray, black hole X-ray binaries, the corona becomes more and more important, and the fraction of power that's released in the corona becomes comparable to the fraction of power that's coming out in the disk. So this RULX model here can be seen as an extension in the accretion rate of the current black hole X-ray binary paradigm, such that if you increase the accretion rate, so here, for relatively small accretion rates, you have thermal disk emission and a highly subdominant coronal component. And that you can call it the high state. If you increase the accretion rate even more, you still have disk emission, and yet now a more important coronal component, and where, roughly speaking, equal powers is being released into each component. And that's a very high state. So you can think of this model as the ULX state, in which the accretion rate is several times the Eddington limit, and now we basically have a flat power law, and the Comptonized coronal emission is the dominant form of gravitational energy, or the dominant spectral component of these sources. And so I will skip this stuff because I'm out of time, and I can just summarize. So let me just summarize. So the coronal energization resulting from non-local dissipation of binding energy is required in order, just on physical grounds, is required in order to get around the trapping problem, or the Eddington limit that has to do with radiative equilibrium. The spectral energy distributions of the brightest ULXs, the ones that are breaking the Eddington limit by a factor of 10, are dominated by hard power law-like, presumably Comptonized emission. This implies that the intermediate mass black hole picture really comes into question because disk emission is not a very straightforward exercise to go from disk emission to black hole mass. And I think stellar mass black holes are more conservative in that respect. And a coronal dominated accretion flow model is what you actually need just on physical grounds to have a high accretion rate that's super Eddington while maintaining a large radiative efficiency. And with that, I'll conclude.
Question?
I think I'm missing something. When you have black holes in the solid state, like direct 915, the temperature of the accretion disk that you see is maybe 1.5 keV, something like that. When you increase accretion rates, when you increase luminosity by another factor of 10, and you say that you dissipate in the accretion disk itself only 10%, it's still 10 to 39 Earths per second. So I don't see how you can get a temperature with all the 0.1, 0.2 keV if you have 1 to 1.5 keV.
Yeah, you are missing something. So, spectral formation of region 2. I didn't have time for this. So again, I didn't cover this part because of the following reasons. That soft thermal disk emission, that 0.1 to 0.5 keV thermal disk emission, is only responsible for 10 or 20% of the total photon power. What?
It's 10 to 39 Earths per second.
Yeah, but for these, the total luminosity is 10 to the 4 Earths per second.
Yes.
Well, because 10 to the 39 is 1/10 of 10 to the 4.
Yes,
Okay, so it's 10%, okay? And so that's why I didn't cover it. But if you wanted to really explain this small subdominant fraction, which people use this component to say that they're intermediate mass black holes, you can. And this is how you can do it. So ironically, if you let me go back to the slide, I have a slide for this. So ironically, a simple way to get out exactly 1 Eddington's worth of thermal power from a black hole accretion flow at an unusually cool temperature is to pump up the accretion rate. This is counterintuitive. And how do you do this? Well, If the accretion rate is larger than the Eddington accretion rate, then the characteristic radius at which you can emit efficiently moves out. And since that characteristic radius moves out, the characteristic temperature goes down. And so that's the answer to your question. Yeah.
Mark?
I would like to remind the second Eddington limit for accretion. You had only mentioned the first one. And Baczynski years ago derived from this hydrostatic equilibrium for accretion, this Eddington limit, a condition that h over r should be greater than factor of the order of unity n dot over n dot critical. And the lesson from this is that if we have super Eddington accretion rates, we cannot have thin disks. So the structure must be geometrically thick, however you call it. Ramesh Narayan is joking that the structure could be called a disk with corona without a disk.
Okay, right. So the corona, okay, the disk where the most of the mass is going to be geometrically thin because you're dissipating a relatively low amount of gravitational power in it. Okay? But the corona, in the absence of all forces, is going to have to be geometrically thick. And the luminosity that's being generated in the corona is larger than the Eddington luminosity. Okay? So hydrostatic balance is going to be busted. It's going to be broken. So there's nothing you can do about it. So it's going to be a relatively thick geometry, the corona, and on top of that, or spherical geometry, and on top of that, there's going to be an outflow. But the real question is, how do you maintain radiative efficiency? Can you get out all the power in photon power, rather than converting the photon power into mechanical power, which is not observable? And the reason why that you can do that in a corona is because a corona is optically thin, almost by definition. So you're right in that the flow will be geometrically thick, but you will not convert all your photon power into mechanical power.
Other question? Carl?
So why do some X-ray binaries do it this way, in UL X-ray, and some the normal way?
Well,
do you have any?
If the accretion rate is very large, so the accretion rate is not determined by the central regions where most of the gravitational power is released. So the idea is, well, the accretion rate is determined by the supplier. The supplier here is the O-star, and in particular the relationship between the gravity of the black hole and the envelope of the O-star. And so if the black hole is either close enough with the O-star at any given time, is willing to donate a large amount of mass to the black hole, then the accretion rate determined at large distances will be relatively large. So.
Any other questions? One more?
In your calculation of either normally considering photonionization, do you have to worry about constants?
That's a problem. That's absolutely correct. So above 20 keV or 30 keV, the albedo is energy. It's energy dependent. So you do have some Compton downscattering. And what they'll end up doing, it will heat the skin of the disk to about a few to 10 keV. So it'll heat the skin to a few or 10 keV down to a few optical depths. And what they'll actually do, that actually might be useful in terms of trying to understand the SEDs, because if the optical depth of the corona is 1 or less than 1, which it has to be, in order for you not to convert all your photon power into mechanical power, if the optical depth is less than 1, and the Y parameter is 1 such that your spectral index is 2, delta E over E per scattering is 1 or larger than 1. So you will see the photosphere of the disk, okay, above 1 keV. So what that might end up doing is it will fill out the region in between the photosphere of the disk and where the power law recovers. So.
All right, well, let's thank our speaker again. Now, I guess officially, we have time for general discussion if there is any interest in it. Marek?
If I remember Benson and Jackson paper, there is no accretion flux in the corona. Is it correct?
Exactly, yes. There's no mass transfer.
So, exactly. So it's very difficult to imagine that you can release all the binding energy in the corona when all the mass flux is in the kind of a thin disk below.
It is difficult to imagine, but it has to happen. I agree with you, it's difficult to imagine, but it has to happen because there's no other way to
Why?
explain.
There are other models which are solving this problem in a different way. Like this which you really described today.
Well, yeah, well, I would say that well, let's say if it was a sub-Eddington black hole accretion flow, ones that we're very comfortable with, like Seifert ones or black holes in the high space, okay, that have 10% or 20% of their power coming out of the corona. The albedo of those disks are smaller, so that means that 10% or 20% has to be multiplied by 2 in order to get the power that's dissipated in the corona. So there you're already up to several tens of percent or 50% of the accretion power that is dissipated in the corona. So before we even knew what ULXs are, we should still have been uncomfortable with that much gravitational power being dissipated in a relatively diffuse region. I mean, if you look in stars, the most coronal, the stars that have the most amount of corona, or the stars that have the largest ratio of coronal power to bolometric thermal power are rapidly rotating stars, and that ratio there is at most 10 to the minus 3. So why is that ratio in stars 10 to the minus 3, but that ratio in disks that we have no arguments about, like Seifert ones or sub-Eddington black hole X-ray binaries, why is that aboard a unity? So, I mean, maybe you can, with respect to the ULX issue, you can say, well, 50% is reasonable, but 90% isn't reasonable. I mean, I'm going to say 50% is unreasonable, but it happens.
Any other topics for discussion? I guess we're worn out.
Solved all the problems.
Well, if not, going once, going twice. Alex, do you want to give instructions about dinner?
The dinner, yes, that's in the room next door. We'll start with the drink. That will be at 6:30. So that's in a bit more than half an hour.
Okay.
And that's all free and included. But only for those who have signed up. I hope nobody bails out in the last minute. That would be a shame because then we still have to pay for those people. Yeah. Any other questions from your side? All right. Good.